Hello, I'm Charlie. In this video, I want to talk about MPS files and how efficient we can parse them. These files are important because this is the main way we represent MIP instances on disk. However, this is a text-based file format, which means we lack strict type safety, and it's also inefficient to store on disk. To address this issue, I've been working on a repo called parse MPS benchmark, where I try to answer the following question. Does converting MIP problems from the text-based MPS format to the binary Parquet format help speed up the Heist solver? So in this video, I'll show some benchmark results to try to answer this question. We are now in the dashboard that I built to try to answer this research question. You can pause this video and read the key takeaways right away, but we will go through the results and discuss them as they come. First thing is the matching rate. This is important because we are solving instances in two different ways. We are solving instances directly with Heist, with its built-in MPS file parser, and then we solve it using the Parquet file that we generated. So there might be an error in our parsing, and so that's why we need to verify if it's valid. A few things to notice. So here we have the objective match. You can see that for some instances it doesn't match. And actually this is not necessarily an issue with the parsing itself, but has more to do with the fact that we have a time limit of 20 seconds to solve the instance. So here we're solving the LP with the simplex, and it's not guaranteed to convert to the exact same solution if we stop the solver after 20 seconds. So if we reach the time limit, there might be some error. That relative difference is small. The places where we don't reach the time limit, this is where there most likely an error. For example, the MAD instance is probably a parsing error. And I think there's another one here, the NEOS dataset instance here. But overall, it's quite accurate. We're above 95% accuracy if we ignore the fact that we have a time limit. Next thing we want to look at is the solve time, which is the main thing we're interested in. So this is the absolute difference. We can see that most of the time we're very close to zero, and given that the distribution is skewed here, I put the mean, median, and the percentiles. Notice that the absolute difference is relatively small. We are around 10 to 100 millisecond gain in absolute difference. Notice that sometimes we lose some performance. We're slightly slower, and this is because there is some Python code to go from Parquet to Heist, some Python code, and that Python code could be the bottleneck in that case, so it should be rewritten in order to avoid that potential performance loss for some instances. But typically we do get some gain. In here we have the relative speed up where we are around 20%. It's probably not a good idea to look at the average here because of outliers, but a gain of about 20% is to be expected in relative term. Finally, I want to look at the Parquet creation time. So how much time it takes to go from an MPS file to Parquet. And this is the main bottleneck with this setup. You can see that it can take almost 10 seconds for 25% of the instances. 10 seconds is quite long, given that we're saving maybe 100 milliseconds. But this is done offline, and it's a one-time cost. And it can be easily rewritten in another programming language. So I should say that there are other advantages of using Parquet. You have a small footprint on disk, and it's a structured data. There's less ambiguity on how to parse the data. You can easily load it, and it's compatible with big data libraries. So even though on these instances, which are really at the end of the day quite small, we can expect to get still some gains, and that gain should be way more significant as you scale the size of the instance, and you get other benefits such as the one I just introduced. So that's it for me today. Thank you for watching. Bye-bye.